Welcome to a fascinating journey into materials that defy our everyday intuition about how matter behaves when heated. Most materials expand when heated, but negative thermal expansion materials actually shrink. This is like having a rubber band that tightens when you warm it up, instead of becoming looser. Let's start by understanding normal thermal expansion before we explore the counterintuitive negative version. First, let's ask, what happens to most materials when we heat them? At low temperature, atoms are packed closely together, vibrating gently around their equilibrium positions. When heated, atoms vibrate more vigorously and push apart, causing the material to expand. This is the normal behavior we observe every day. The coefficient of thermal expansion, alpha, measures how much a material's length changes per degree of temperature change. For most materials, alpha is positive, meaning they expand when heated. Typical values range from 10 to 30 parts per million per Kelvin. Now let's explore the surprising phenomenon, where some materials actually shrink when heated. What happens if the thermal expansion coefficient is negative? The material contracts instead of expanding. At room temperature, the NTE material has a certain size with atoms arranged in a specific structure. When we heat it to 100 degrees Celsius, instead of expanding, the material actually shrinks. The structure becomes more compact, defying our everyday experience. The coefficient of negative thermal expansion can range from -10 to -100 parts per million per Kelvin, which is quite substantial. Let's look at a real material that exhibits this fascinating behavior, zirconium tungstate. Zirconium tungstate, with the formula ZrW₂O₈, has a thermal expansion coefficient of -9 parts per million per Kelvin over a wide temperature range. The structure of zirconium tungstate consists of zirconium, tungsten, and oxygen atoms arranged in a complex three-dimensional network. Let's do a numerical calculation. If we heat a 10-centimeter sample of zirconium tungstate from 0 to 1000 degrees Celsius, how much does it shrink? The change in length equals the original length times alpha times the temperature change. Substituting our values, 10 centimeters times -9 times 10 to the -6 times 1000 Kelvin. This gives us a shrinkage of 0.09 centimeters, or about 0.9 millimeters. That's almost a millimeter of contraction. Now let's understand the physics behind this counterintuitive phenomenon. Here's a great question. If atoms vibrate more energetically when heated, why would the overall material shrink instead of expand? The answer lies in the structure. Some materials have flexible bond angles that change more easily than bond lengths. In NTE materials, transverse vibrations, those perpendicular to the bonds, dominate over longitudinal vibrations along the bonds. When cold, the bonds between atoms are relatively straight, keeping atoms far apart. When heated, increased transverse vibrations cause the bonds to bend more, bringing the end atoms closer together even though the bond itself doesn't shorten much. The effective distance between atoms decreases approximately as the square root of 1 minus theta squared over 2, where theta is the bending angle. NTE is most common in materials with open framework structures. Framework materials have open cage-like structures with lots of empty space. This openness allows for the flexibility needed for negative thermal expansion. Examples include zeolites, which are porous aluminosilicates, metal organic frameworks or MOFs, and certain ceramic materials like zirconium tungstate. Let's examine this from an energy perspective to understand why it's thermodynamically allowed. You might wonder, doesn't shrinking when heated violate the laws of thermodynamics? After all, we're adding energy, but the material is getting more compact. The answer is no. While the material shrinks, the entropy of atomic vibrations still increases dramatically. The Helmholtz free energy F equals internal energy U minus temperature times entropy S. The increase in vibrational entropy is greater than any decrease in configurational entropy from the smaller volume. The system gains more entropy from increased vibrations than it loses from occupying a smaller volume, so the total entropy increases and the second law is satisfied. Negative thermal expansion becomes even more interesting in nanomaterials. In nanoparticles, typically 1 to 100 nanometers in size, surface effects become dominant. At the nanoscale, the surface-to-volume ratio is enormous. For a 10 nanometer particle, about 20% of atoms are at the surface. The surface-to-volume ratio is inversely proportional to the radius. Smaller particles have proportionally more surface. Surface atoms have fewer neighbors and different bonding, leading to different thermal expansion behavior than bulk atoms. The overall thermal expansion of a nanoparticle is a weighted average of surface and bulk contributions. Gold nanoparticles, which normally expand in bulk form, can show negative thermal expansion when reduced to a few nanometers due to surface contraction dominating. This unusual property has valuable practical applications. One major application is creating zero-expansion composites by mixing normal and NTE materials. By carefully balancing the proportions of materials with positive and negative thermal expansion, we can create composites with essentially zero thermal expansion. The composite thermal expansion coefficient equals the fraction of component 1 times its alpha plus the fraction of component 2 times its alpha set equal to 0. These zero-expansion materials are crucial for optical instruments like telescope mirrors, satellite components, and precision measuring equipment where dimensional stability is critical. Let's look at cutting-edge research in this field. Researchers are exploring negative thermal expansion in two-dimensional materials like graphene and transition metal dichalcogenides. Recent discoveries have found materials with record negative thermal expansion coefficients of minus 200 parts per million per Kelvin, more than 20 times larger than zirconium tungstate. Scientists can now tune the amount of negative thermal expansion by applying pressure or introducing dopant atoms into the crystal structure. Let's summarize the key concepts about negative thermal expansion in nanomaterials. Negative thermal expansion materials shrink when heated, with thermal expansion coefficients less than 0, typically ranging from minus 10 to minus 100 parts per million per Kelvin. The mechanism involves transverse vibrations and flexible framework structures, where bond angles change more easily than bond lengths. The effect is enhanced at the nanoscale due to the high surface-to-volume ratio and different behavior of surface atoms. Applications include precision instruments, zero-expansion composites, stable electronics, and advanced optical systems. Think of it like molecular origami. When you shake it more vigorously by adding heat instead of flying apart, it folds into a tighter, more compact configuration. Understanding negative thermal expansion opens doors to creating thermally stable technologies that maintain their dimensions across wide temperature ranges.